So let's welcome Steve to give the second talk on Primal-dual coordinate methods for robust machine learning. So Steve, please.
Thank you, Kim Chuan. All right, so I'm going to do some cuts on the fly to make sure I don't go over this time. Okay, so here's another picture of Madison that I did not take, but that's the lake that we sail on there. The campus is in this area here. That's the state capital of Wisconsin. And the previous picture of the sailing dock was taken around about here. That's where the dock is. So the student union is, I think, might be that building there. It's on the lakefront. So anyway, it's a beautiful city in summer at least. So if you haven't been to Madison, you should come visit. Yeah, summer is fantastic. Yeah, and winter, of course, you can walk on the lake then. So it's sort of a little bit different. Yeah, you can skate and everything. Okay, so all right. So this talk is about something more specific and more recent work on convex-concave saddle point problems. So I'll describe the problem, the particular paradigm that we're using. I'll talk about some special cases and then talk about algorithms. So there were 3 papers here, and most of the time is spent on the first one, the pure CD paper. And this is really Ahmet's work. So Ahmet is here right in the middle of the audience. So this is mostly his work. Also, Volkan is one of the co-authors of that paper. And the other 2 papers, VRPDA and CLVR, or Clever as we call it, that's with Yelena and Xiaobing and Eric Lin. And, Yelena and Xiaobing are big contributors to that work. Yelena is my colleague at Madison. Xiaobing is our former postdoc, now works for Huawei. Okay. So these are the 3 papers. One of them was just in NeurIPS last week. The second one about Clever. The first one is under review, and the last one was in, which is about VRPDA. That was in ICML last year. Okay, so here's the problem that we're working with. We've got a function L, which is a function of 2 sets of variables, x and y, and we're looking for a saddle point for L. So a min with respect to x, max with respect to y. And L has a very specific form. So the coupling between x and y is bilinear. So the coupling is through a matrix A. And moreover, the y, there's also 2 convex terms. So h star and g are both convex functions of x and y. And h star is actually separable. So h star consists of a sum for I equals 1 to n of hi star of yi. So it's separable in the components of y. So there are n components of y, so there are n of these hi stars. And the star represents a convex conjugate. So those of you that know convex analysis, Terry Rockefeller's book, you'd be familiar with the definition of convex conjugates. It's defined like this. Supreme over S of St minus Hi of S, where S and T are scalars in this case. So the G of X, that's convex also. It might be extended valued, so it could be infinite for some values of X. In some of the analysis, we'll assume that G is separable also. But in general, we'll assume that G is just a general convex function. And the A is a matrix. It's going to be a n by D matrix. N is a number of components of Y. D is a number of components of X. And I'll use AI to denote the ith row vector of A. So there's a very specific form here. It's clearly convex concave, okay? But a little bit more about the specifications. I'm going to assume all of these algorithms are going to evaluate prox operators. So given a convex function, you can define this prox operator at a point x by solving a little subproblem, which is the min over u of 1/2 u minus x squared plus g of u, where g is the function you're taking the prox of. So this is a ubiquitous operation in algorithms for non-smooth, convex optimization. Now, there's a little bit of a twist here in that we take weighted prox operators. So instead of that u minus x 2 norm squared term, we actually have u minus x weighted by a diagonal T inverse. So T is a matrix with positive elements on its diagonal. And we're going to be making different choices for T. So the notation there is the prox depends on the matrix T and the function G. Okay? And very importantly, all of these algorithms need to compute these operators, so we have to assume that you can compute these relatively inexpensively. Okay, that whatever they are, you can do it cheaply. So In this case, particularly if G is separable with respect to the components of U, then this whole problem of finding the procs, it boils down to just solving D scalar problems. And obviously you can do that pretty easily. Okay. So this looks like a very specific paradigm, particularly because we've got this bilinear coupling of X and Y. But it turns out there's a whole bunch of problems that can be put into this form. And a lot of problems in data science and ML, which is a big part of the theme of this workshop. So for example, first of all, if you go back to the way that I've written it here, and stare hard at the terms in this first sum, in the square brackets here, you can see that, I can really replace AIX inner product with YI, or AIX times YI, because YI is just a scalar, minus HI star of YI. If I take the supremum over the Y and use the definition of a conjugate, that actually boils down to something much simpler, right? I can express it all in terms of X, like this. Just a sum of HI of AI times X, the I throw of A times X, plus G of X. So that's, it's equivalent, the min-max problem is equivalent to this minimization problem that we call ERM. The reason we call it ERM, stands for empirical risk minimization, is that this problem is ubiquitous in data science. So if we choose the HI, for example, to be the argument minus BI squared, this is just a linearly squares problem. The G of X could be some sort of regularization term. If we choose the HI to be the absolute value of the argument minus BI, then it's an L1 regression problem. We can choose all other kind, robust regression problems like Huber losses, things like that. If we choose the HI to be a hinge loss, that is it's 0 if T minus BI is negative and T minus BI if T minus BI is positive. That's a hinge loss that shows up all over the place in machine learning, in loss functions for neural nets and SVM and so on. If we take the GI, if we define the G to be a multiple of X, 2 norm of X squared, that's so-called Tikhonov regularization, very classical technique for smoothing out the solution of a least squares problem, making it less sensitive to perturbations in A and the right-hand side B. We can use L1 regularization. That became very popular when compressed sensing came along. Tibshirani has this famous paper on the lasso in 1997 that basically uses linear least squares plus an L1 regularizer. We can use TV, total variation regularization, if we're doing image processing. We can also do logistic regression in this form, linear logistic regression, least absolute deviation. There's a whole ton of problems. They're basically all the same in that they use some sort of a linear model, right? So the AI times X, that appears linearly. The model, that part of the model depends linearly on X. Okay. But still there's a plethora of problems in that area. Here's a second case that you can put into this form. Suppose you're trying to minimize a G subject to AI times X belongs to some set C. Now C is a subset of the real line because AI times X is a real number. So if C is just a singleton BI, this is just a linear equality constraint. If CI is a half line, it's a linear inequality constraint. Okay, so you can see that you can write it in this min-max form by basically making the max, if you've got all inequality constraints, the max is over all non-positive values of the vector y. So you can put it into min-max form by rewriting it like this. Okay? So it's another special case. Now remember I said that in order to apply the algorithms that I'm going to talk about, you need to be able to compute prox operators cheaply with respect to the G and the H star. And so we can't just have any convex function G here. We have to make sure that whatever G is, it's something we can get a prox operator for easily. And that's true if G is linear. It's true if G is separable in the components of X. It can also be true if G is a convex quadratic. We can redefine the QP in the way by bringing in some intermediate variables to make it, to put it into a useful problem of this form. Okay. By the way, if it's linear programming, that special case, which we're going to come back to, what does the prox operator for G look like in that case, the weighted prox operator? Well, if G is actually G transpose X, then if I plug it into the definition of the prox for that particular G, it becomes separable. And in fact, I can write down the solution of the prox in closed form. It's just xi minus tii times gi. So it's trivially computable in that case. Now, You remember in my previous talk, I talked about concepts of finding epsilon accurate solutions. So we're going to talk about what that means for this problem. But if we're talking about the special case of this linearly constrained optimization, there's a very natural way to define what it means to be epsilon accurate. And that is that the point that you find, let's call it x out, is within epsilon of being optimal for the objective, and it's also within epsilon of being feasible for the constraints. So there's a very natural way of defining what it means to be approximately optimal here. And so when we talk about our algorithms, we're going to talk about how does the complexity of solving the problem, how many iterates do we need to find a point x out that satisfies these properties. That would be an appropriate thing to study if we're interested in this particular class of problems. So the third special case, again, this is a special case of the big problem that we're talking about, is something we call generalized LP. And this is what we used in the CLEVER paper, the CLVR method. And this looks a lot like regular linear programming. You've got a linear objective, C transpose X, but there's an extra term, R of X, which is a regularizer. It could be nothing, it could just be vacuous, or it could be something like a 2-norm, multiple of 2 norm squared. So people have been, even since the early 60s, Oliver Mangasarian had papers on LP with a 2-norm perturbation. So that is a known paradigm. And the other thing that's different from regular LP is that I've got X belonging to some set curly X. And of course, if curly X is just the non-negative orthant, then that's just the standard form constraints for a standard form LP. But it could be something else, as we'll see. I'll give you an example of where X could be something else. Whatever X is, it can't be an arbitrary convex set. Again, we have to be able to compute prox operators efficiently. But here, the prox operator that I'm going to use for this problem, the X, the curly X enters into the definition of the prox. When we take when we solve that argmin problem for a given function R to find the prox, we only take the min over Z belonging to X. And so whatever that set X is, it's got to be something for which we can compute that efficiently. Typically in order, D operations, okay, in order to make these algorithms practical. If you have to spend an enormous amount of energy just computing this prox, then these algorithms are not going to be that useful. All right, so here are some special cases of this paradigm. Even this paradigm, which is a special case of the general min-max problem, which is given here, by the way. This is how you put it into the min-max form, okay, that I had on the first slide. Even this subset of the general min-max problem has a lot of interesting instances. For example, ordinary LP, if I just set the R to be vacuous and the X to be non-negative orthant, I just get standard form LP. Reinforcement learning, everyone knows that reinforcement learning, the classical paradigm of Markov decision processes, you can write that as a huge LP. So in that sense, that's a special case of this. Optimal transport, you can write like this. Distributionally robust optimization for certain choices of the divergence measures, you can write them in this form. I've got a little bit more about that coming up. And even there's a recent paper on relaxed neural net verifications. These are problems that you can solve to verify that the neural net is doing what you want it to do. If you relax those problems, they're hard problems, they're combinatorial, but if you relax them, you get a problem of this form. So there's some special instances just of this form. A little bit more on the distributionally robust example. I want to convince you that that's a special case of this generalized LP. So what is DRO? Probably most of you know what DRO is, but I'm going to describe what it is in a very specific instance here, where the problem that we're solving is one of these finite sum problems that comes from machine learning. So the objective is going to be an average of H of BI times AI transpose W. So what's BI? BI is a label, plus or minus 1. AI is a training example, a vector of features. And W are the parameters in this linear model. So this could be, for example, a linear support vector machine or something. Okay, classical linear SVM. You've all seen the picture of two clouds of points, red points and blue points, and you're looking for a plane that separates them. Okay, so it could have this form. Now, DRO, it sort of takes the viewpoint that the data that we're given, the n items of data that we're given, is some draw from some true underlying set. So what we'd really like to find is a W that neatly satisfies these two underlying distributions of the two classes. And all we're seeing in the training data is a particular random draw from that distribution, okay? Because we can't know the whole distribution without having an infinite amount of data, typically. So what DRO tries to do is it sort of says, let's not focus on separating this empirical random sample, but let's do something a little bit more sophisticated. Let's assume that what we're seeing in the terms of this n item of data is some finite distribution Pn, is given by Pn here, and the true underlying distribution is some other distribution P. But we're going to assume that the true P, which we don't know, is within a ball of radius rho around the Pn, okay? So instead of just solving the problem, the minimization fitting problem over the Pn, what we do instead is to say, let's look at all the distributions in this ball around Pn, and we hope that the true distribution is somewhere in that ball, and let's minimize, instead of this finite sum over all the empirical training data, let's minimize the expectation with respect to P belonging to this ball of this loss function, okay? And we're going to choose the W to do as good a job as possible in the worst case over this ball of this expected loss. So it's a little bit fancier than just blindly minimizing over the empirical training examples. Now you might look at this and say, well, yeah, this is a really hard problem because these distributions, they have infinite support. I want to compute an expectation of this function over this whole distribution set. Seems like it's really hard. But if you define the distance between, this depends on a distance function between two distributions, you can define that in different ways. If you choose certain ways to define that distance function, you can actually come up with closed form formulations of this very difficult looking problem at the bottom of the slide here. So in particular, if you define the distance between distributions to be the Wasserstein 1 norm, this problem at the bottom of the slide has this particular form, okay? So I don't think I can work through all the kind of specifics of this. We have to introduce a bunch of like auxiliary variables and so on, but it does have this general LP form. You can see for a start that clearly it's linear in the variables. Rho is a parameter, lambda is a variable, the SOIs are auxiliary variables. You can see that all these constraints are linear as well. The first three constraints are linear, which is what we had here in the GLP form. And the last three constraints, you can think of these as being the X, as defining the curly set X. And these are separable, okay? Because the W norm, infinity norm on W constraint, that just breaks down to bounds on Wi, the components of W. So basically you can separate these last three constraints into n little, individual polyhedra. And so you can do a prox operators, it basically satisfies this assumption that we made here, that you can solve this problem pretty easily because it separates down into little three-dimensional problems. Okay, so this is one example of where this general LP paradigm works well. All right, so I've given you the general problem, which I've stated again here, just to remind you what it is, finding a saddle point of this function L, and I've given you a bunch of different instances to sort of try to convince you that it's a useful paradigm to look at. So now I'll talk about algorithms. Okay, so maybe the most basic algorithm is this gradient ascent descent, or descent ascent. I don't know, I've got to call it GDA, so I suppose that's gradient descent ascent. So basically what that says is we're trying to minimize with respect to x. So let's take the gradient of L with respect to x, and we only do that for the bilinear term. So when we take that gradient, we get A transpose Y. And then we take a step in the negative gradient direction, and then we use a prox operator to explicitly account for the G term, right? So we're not approximating the G by a linear, approximation or anything. We're explicitly accounting for it by using the prox operator. We're taking it very seriously, okay? So this is like, it's a sort of, the sparser algorithm and that we worked on years ago in compressed sensing. Basically, it's a prox gradient approach applied to minimizing with respect to x. So you take a step like that to minimize with respect to x, and then the second step is you maximize with respect to y. So you take that latest x iterate that you just generated, you can compute the gradient of L with respect to y, and you get AX, and you take a step in the positive gradient direction because you're trying to maximize. And then you use the prox operator to explicitly account for the H star term. Okay? So this is just naturally taking gradient steps in the max and min variables, and then using prox terms to account for these extra convex functions that are added on for certain choices of step size. So this is maybe the most obvious extension of steepest descent to this kind of a case. And this method is, people thought of it a long time ago, and there are analyses for that method. But in 2011, Chamboul and Pock came along with this other method called Primal-dual hybrid gradient, which turns out to be much more powerful. And it's similar to the GDA. In fact, in the step in Y looks identical to GDA, but the step in X is a little bit different. Instead of A transpose Y bar K there, we add on this term, which is A transpose Y bar K minus YK minus 1. So it's like the difference between the last two gradients with respect to X. So that probably reminds you of what we do in a momentum type method like heavy ball, where we sort of do something with the last step and we sort of keep heading in that direction and then add on a little bit from the current step. So it has the current gradient. So it has that same sort of spirit. In fact, if you introduce an extra variable called X hat K plus 1, you can reformulate this two-step procedure equivalently like this with like a three-step procedure. And the first two steps are absolutely the same as GDA, right? They look almost the same as GDA. The only different thing here is that instead of X bar K here, we have X hat K. And we get X hat K by making this little correction in the third step to X bar K. So it's like GDA, but you're stepping away from a different value of XK. Okay. Now, in the original Chamboul-Pock paper, they talk about how this is connected to all these other methods that have been previously proposed, like Douglas-Ratchford, extrapolated gradient, ADMM, and so on. So they sort of point out that it's actually connected to a bunch of other powerful techniques that have been around. Okay, so all of the methods that I'm going to talk about in my remaining 22 minutes and 31 seconds is basically build on PDHG. Okay, so but they add on all these extra features to try to make it improve the complexity, to try to fit it to the specific form of the problem that we're the interesting variants of the problem that we're talking about, and so on. And I'm not going to bombard you with all the analysis and everything. In fact, I'm not even going to tell you a whole lot of the details, but I'll just point out some of the things you can do with this basic method here that could potentially make it more practical. The first thing you can do is that you may not want to update the entire vector y in that step 1b. You might want to just pick a random component of y. And you can do that because remember the H star is separable. So if I just want to update a single component of y, I just have to do that prox operation with respect to the HI star. Okay, and leave all the other components of y alone. So that's one thing you can do. Another thing you can do is variance reduction. So you can say, look, if I'm going to only update individual components of y, that means that I'm going to introduce a lot of kind of messy variation in the gradient with respect to x. So this A transpose YK term is now is kind of messed up by the fact that you're not seriously updating all of y. And so you might want to average over a bunch of different y's before you take that gradient, okay, to sort of smooth out the gradient steps in x. So that's one thing you can do. A similar thing you can do is that you can sort of average the gradient over all the previous iterations. It's almost very similar to the variance reduction idea. Other things you can do, remember I mentioned that we were going to be using these weighting matrices in the prox operators. Essentially what that means is that instead of taking the same step in all the components of x, for example, we could take weightings in those steps. We could do some sort of importance sampling. And Peter did, more than 10 years ago, Peter Richterich did this in the context of stochastic gradient coordinate descent methods and got better complexity results by taking weighted step sizes. And you can also do iterative averaging. So you're going to generate a sequence of x's, a sequence of y's. You might not want to output the last element of the sequence. You might want to take some sort of a weighted average of all the iterates you've seen so far. So these methods, our three methods here, use these different ideas in different ways. Okay. So I already told you, there's this issue that comes up that I mentioned in my first talk of how do you decide you're at an epsilon accurate solution? And I described how to do that in the special case where we were minimizing a convex function subject to linear constraints. But for the general problem involving the min-max involving the L, what's a reasonable way to decide when we're at an epsilon accurate solution? That turns out to be a sort of a little bit of a complicated issue. And this might be a one place where I can cut a little bit. But the way we go about it in certainly in the paper, in Amit's pure CD paper, is we define this function g, and it takes as input two xy pairs. There's xy and x prime y prime. And we take the difference of L, evaluated at x prime y and xy prime. And basically, that just gives us a difference between two versions of L evaluated at two different pairs of points. And then we take the gap function to be the max of that over all of the xy's in some feasible set. So what are we trying to do? Well, we're trying to pick the y to make that first term there as big as possible, right? And we're trying to pick the x to make the second term as small as possible. So we're trying to pull those two versions of L as far apart as we can, right? We're picking the xy to pick those as far apart as we can. And we're going to take that to be the gap that's defined by the current x prime y prime pair. Okay, so essentially we want to iterate until that gap falls below some epsilon. Now there are a couple of ways to do that. You can either take the max of the expectation. So what am I talking about here when I talk about expectation? All these algorithms I'm going to mention are random algorithms, just like coordinate descent, just like stochastic gradient. At every iteration, you're doing something random. You're picking a random coordinate or random component of the gradient. And so every time you run the algorithm, you're going to get different results. And so we have to think in terms of what's the expectation of what's happened after k iterations. Where can we expect to be in terms of the algorithm's progress? Now, the question arises, we've got to take an expectation and we've got to take a max in order to define this gap function. So what order do we do those things in? So if we take the expectation first and then the max, that gives us one measure. And in fact, in our VRPDA paper, we prove a complexity result for that measure. It's actually better to take the max first. That gives you a stronger result. Now, the reason is that if you take the expectation first, xk, yk, your current iterate, can actually be a quite infeasible point, a very suboptimal point. But the expectation will make it look like a good point somehow. And so this might be a misleadingly, you might be able to reduce the max of expectation below some small epsilon, but it might not be that good of a approximate solution. The second one is much stronger, where you take the xk, yk, you try to make the gap as big as possible, and then you take the expectation over the randomness in the algorithm after that. And so the results for pure CD, we use that second measure, which is a better measure. Okay, when we're doing complexity analysis, what are we looking for? Well, we want to reduce this, whatever criterion we're using here below epsilon. So clearly we want to express the number of iterates in terms of how they depend on epsilon. But there are also other terms that I'm not going to gloss over here. We're also interested in how that number of iterates depends on the dimensions of the problem, D and N, how it depends on some measure of the size of the matrix. So the norm of A, for example, or we could take the maximum of the norms of the rows of A, or the sum of the norms of the rows. All of those different quantities show up for different algorithms. We're very interested in the sparsity in A. So we might want to figure out how the complexity depends on the number of non-zeros in A. And also we want to get a handle on how does it depend on how far, what's the distance between the starting point and the solution. And all of those things show up in our complexity bounds. And again, I want to point out, and this ties in with the theme of my last talk, that some methods like stochastic PDHG, which is a stochastic version of PDHG, as its name suggests, their bounds are not so impressive, but it behaves quite well. So complexity bounds are not the whole story here. They don't necessarily tell you what the best algorithm in practice is. Okay, so most of what I've got to say in the remaining time is about pure CD. And the reason we like to focus on that is it's the last of the three algorithms, and it's the simplest. It really is very close to basic PDHG. And yet, we can prove these quite strong results about it. So this is the whole of the pretty much the whole of the only thing I was swept under the rug here is the initialization, I guess. But it's pretty much the whole algorithm. So it's the same as PDHG. The only difference is that in lines 3 and 4, we're just updating a single component of Y. And the other difference is that we're using diagonal weight matrices all over the place. So in that line 3, we've got a TK there, which is a diagonal weighting matrix, instead of the constant tau. And then in the updates to the X, we've got a weighting matrix P, which defines the probability that we choose component I of Y to update. And we've got the TK again, and we've got another diagonal matrix theta K. And the art of this method is how do you choose the TK, the theta K, and the P? Okay, all of these things are kind of important to getting the complexities that we want. Now, there's a little bit of notational stuff here that I'm very proud of this, that when I've got this notation with a square bracket, subscript ik, that means that formula only applies to the ik component of the vector. And the backslash ik means that formula applies to all the components except for ik. So it's a compact way of saying that I'm only updating one component. Okay? So that's pure CD. That's the whole algorithm. Okay? And one thing about it is that each step of this algorithm only takes order D operations. If you look at all of these steps, you can figure out that it's pretty easy to implement it in a way that the number of operations, the number of arithmetic operations is only order D. Okay, and there are a few details there. The thing we output is not the last iterate, x bar k, but it's the average of all the iterates you've seen so far. Okay? There are versions with, if you really want a yk, you can compute a weighted average of that, but often in these problems we only care about the xk. And as I've already mentioned, it's very similar to PDHG. So what kind of complexity results can we get for that? Well, going back to the special case of linearly constrained convex optimization, we can prove that you can get these two quantities that we care about, which is the suboptimality and the distance to feasibility. These basically go down like 1 over k. So this is like a 1 over epsilon type complexity. And moreover, we can get a very concrete handle on how they depend on the size of A, as measured by the sum of the row norms. The D1 and D2 are measures of how far away the initial point is from the solution. And this gamma is a constant that shows up, it's a constant between 0 and 1, that shows up in how you choose the T and the theta K and so on, which I'm sweeping under the rug here. So basically there's 1 over K converges. All this assumes about the G and the H star is that they're convex. It doesn't assume any strong convexity. In the case where we've got a general problem that's not constrained optimization, again we get sort of a 1 over K rate for that case. Here the dependence on A is different. It's the maximum row norm being the sum of, rather than the sum of row norms. But there's an ND term in there, which isn't present in the special case of constrained optimization. This is an estimate, by the way, of the computational complexity. It's not the number of iterations. It's the actual computational complexity of the method in terms of flops. Okay, now we thought really hard on, in fact, this work was partly motivated by the fact that when we were doing numerical experiments for the VRPDA, we found that on sparse matrices, we didn't have an analysis of what pure CD did on sparse matrices. And there was no obvious way to specialize it in the case where A was sparse. So this led us to think about how can you tweak the pure CD method I showed you a few slides ago to really exploit the sparsity in A. And this version does that. It's only marginally more complicated. The main difference is that the update, we define this quantity J of I that tells you the locations of the non-zeros in row I. So that's how I define J of I up here in this first term. And when we do this step of updating the X, we only update the components that correspond to the non-zero locations in row IK. Because IK was the element of Y that we're going to change at this iteration. Okay? Now, if you stare at this long enough, you might think, well, isn't this just the same as what pure CD would do with a sparse matrix? Turns out it's not quite the same. The way we update the X bar K in line 3 there actually gives us a different result for pure CD from the sparse form of pure CD. So it actually is a different algorithm, and it needs its own analysis. Here I'm going into a little bit of detail here, but suffice to say that we did have to kind of redo the analysis for this case because it was a different algorithm. It's equivalent in the sense that if you give the sparse pure CD algorithm a dense matrix, it does produce the same results as applying the original pure CD. But if you give it a sparse matrix, it gives different iterates to if you applied the original pure CD on the sparse matrix. Now, the main difference in the results is that you no longer get, going back here, I've got this ND thing that shows up in the computational complexity. Essentially what happens, and ND would be the number of elements in A if A was completely dense. Essentially what happens is we're able to replace that with the number of non-zeros in A, which is the sort of result we would like to see, right? So this result here, for example, has got an NNZ of A. Now in this case, there's a bunch of special cases. Not only do we do the case where G and H are just general convex functions, we also do analyses for the case where one or both of those is actually strongly convex. And then you can get stronger results. In fact, if they're both strongly convex, you end up with a log epsilon dependence rather than a 1 over epsilon. So a much stronger result in that case. In the case where one of the two is strongly convex and the other one is not, we get a 1 over square root of epsilon rather than 1 over epsilon. So we can get a slightly better result in that case. Yeah. Stochastic primal-dual average gradient. So you want to go back to yeah. Hold on, I've got to find it. This one here. Okay. Stochastic primal. I don't even remember what that is, but it's averaging the gradients in the y. Is that what it does? The what? The reflection of x, you said? Okay, so it doesn't do that. So it's that sort of momentum term there that's different. Okay. Yeah. Right. Yeah. Okay. All right. So I have 7 minutes left. So let's see. Just a few. There've been a lot of other algorithms for these problems, starting with PDHG. There's a stochastic form of that. There's VRPDA, which is the earlier version of VRPDA2, which we worked on. A bunch of others, including Katyusha. Katyusha is a very, very complicated algorithm. It takes like more than a page to write down. But in any case, pure CD, we believe that we can match or improve the complexities of all of those earlier methods in terms of their dependence on N and D, the different measures of size of A and epsilon. Okay. Sometimes these measures, these improvements are sort of modest. So we can, for example, we can change a norm of A to being a maximum row norm of A, which is it's an improvement, maybe up to a factor of square root of N, but it could be a modest improvement depending on the sort of A that you're dealing with. Just a comment on the proofs. They're extremely technical. People like Ahmed are absolute wizards at learning the tricks and being able to manipulate inequalities and all sorts of very inventive ways. But the details are very complicated. There's a lot of telescoping sum arguments that come in there. And the other real expertise comes in choosing these weighting matrices. You have to choose them in certain ways to get the desired cancellations when you do the telescoping sums. So I'm mercifully sparing you all the details of that. Okay, so that was mostly about pure CD. Just a few words about the other two methods. So this is VRPDA2. So this was earlier. This was middle of, we wrote this sort of 2 years, early 2021, I guess. Now, when you look at this, it looks immeasurably more complicated than pure CD. But if you pick it apart, you can sort of see things in there that look sort of familiar. First of all, the motivation is different. It's based on these sort of estimate sequences that that Nesterov uses a lot in his 2004 book. It sort of uses that style of analysis to sort of bound the primal and dual versions of the function. The other thing is you can sort of recognize in some of these lines some of the elements that you see in PDHG. For example, line 8, it looks like that extrapolation step that you see in the third line of PDHG. Step 4 looks like a coordinate update step where it turns out that you can implement line 9 by just solving a scalar problem to find yik. It looks like I'm minimizing over y, but it really is just over yik. So that looks like a coordinate update step for y. The zk is kind of a gradient averaging step in line 11. And then line 10 is kind of the x updating step. That you can sort of express that in a different way as it looks very similar to the updating step for x in PDHG. So if you sort of look at each of these lines hard enough, you'll recognize that they actually do kind of descend from PDHG with a lot of sort of little tweaks. One particular tweak is how you choose in line 8. You've got this ratio of ak minus 1 to ak. Now this ak is a scalar sequence that's generated in line 12. And that's where some of the magic comes in. You don't extrapolate just by a factor of 1, but you extrapolate by this very specific term. And there's a lot of expertise goes into choosing exactly how you define the AKs to make it work. Okay, and the sorts of results we get for that, somewhat similar to pure CD, except that in pure CD we can exploit, VRPDA2 can't exploit the sparsity. And so in pure CD, the sparse version of pure CD, we're able to replace the ND with a number of non-zeros in a term. So pure CD came later, so it's a bit of an improvement on this. Now the Clever came in between VRPDA and pure CD. So Clever said, let's not try to solve the original min-max problem. Let's just attack that generalized LP, that special case that I mentioned, and I showed you that DRO was a special case of that. For this special case, we can simplify VRPDA2. So we just took VRPDA2 and simplified it to take account of what was going on here. The big thing that's different about this special case is that the y, there's no h star of y term. And so when we take the maximization over y in the min-max formulation, it's an unconstrained maximization. So it simplifies a lot of things. And so the algorithm already looks a lot shorter. And there are a few notes on that there. And basically we have to make this work for sparse matrices, which you can do. You can make Clever work for sparse matrices, but it's a lot of messing around. You have to introduce this thing of lazy update. Rob knows all about lazy stuff. But you have to sort of do a lot of bookkeeping to be able to implement the different steps of this in a way that's sort of order D operations per step of this method, which I'm omitting. In pure CD, that's much more natural to do. It's much easier to do in pure CD. Here we have to do a lot of bookkeeping, but we end up with nice results, basically very similar to the pure CD results. So finishing up, magically I'm almost going to be on time. We actually implemented Clever, these are mostly for Clever and pure CD, on that DRO formulation that I showed you earlier, that robust hinge loss with a Wasserstein 1 norm and so on. We got results on that generalized LP. And we compared to PDHG, the original PDHG, the stochastic PDHG, and then 3 versions of our methods, the pure CD and Clever, 2 versions of Clever, one where you just update a single component of Y on each iteration, and another one where you pick 10 components of Y to update at random. So you do sort of a block coordinate update on Y. And it turns out that blocking actually makes it perform better. So the blue line, the second plot here is for time. Obviously, by doing the blocking, you get about a factor of 3 improvement in runtime. Pure CD doesn't have any blocking, but we could just as easily do it for pure CD. So the takeaway from this is that stochastic PDHG does pretty well on this, but our 3 algorithms are potentially better on that problem. This problem, there's a bigger difference between our methods and the 2 older methods. You can see in the runtimes are a sort of factor of 2 or 3 or 4 times faster. And similarly, RCV1. By the way, all of these were standard data sets, RCV, GSET, and A9A, sort of modest-sized data sets that we turned into by two two-class classification problems, and then did this robust DRO one. Now, we got very brave here and tried, oh, I'm out of time, but I'm almost finished. We got very brave and tried comparing this with Gurobi, a production quality LP solver. And we just compared Clever with Gurobi. Now, two of the cases we were at least competitive. The last two improved by maybe a factor of, well, I don't know. I guess at most 2, if I'm being optimistic here. But we were competitive. The first one we got absolutely killed by the barrier form of Gurobi, but we got an excuse for that, and that is a lot of the power in Gurobi is in the pre-solve. And any of you that worked with LP software know that the pre-solve is absolutely critical. It can reduce the size of the problem, the number of constraints, number of variables enormously. And in fact, in A9A, the pre-solve vastly reduces the formulation by about a factor of 5. And that's why we get killed, because we don't do any pre-solve in our version. I think I'll skip the last one. Just make some final comments. So there's a quote by Dijkstra that says, this goes back to the 60s, I think, simplicity is a great virtue, but it requires hard work to achieve and education to appreciate. And to make matters worse, complexity sells better. And I think this quote could be applied to a lot of modern ML research. Peter was just telling me over the break that he's got a much simpler analysis now of random reshuffling and stochastic gradient that can fit on a page, whereas prior analyses are extremely thorny and complicated. And so I really believe that simplicity, distilling things down to their essence, trying to come up with the simplest form of the method, the simplest analysis is a really worthy goal. Now, we believe that pure CD is a very simple method. The analysis is still quite complicated. So there's still work to do to try to simplify that. And that begs the question, can we do that? Can we make the analysis easier? Or can we come up with different measures of complexity that admit a simpler analysis? Okay, thank you very much. I'm sorry I went over again. Thank you for listening.